My name is Mariusz Dąbrowski. I am the president of Jerzy Stelmach Eureka Foundation, which deals with popularization of science and in particular popularization of the frontal scientific research. The foundation gathers active scientists, and this is why we want for a couple of days offer you lectures and debates under the project Science Closer to the Society, session 5, devoted to classical and quantum black holes in the universe. Our project is co-financed by the Polish Ministry of Science and Higher Education under the Social Responsibility of Science Program 2, and its aim is to bring the achievements of outstanding scientists to the general public. Our session is held in English and in Polish. English part, and in particular these debates which are held today, and the final discussion will be translated into Polish and placed on YouTube in 2 or 3 days. I would like to remind that we have heard 3 lectures now. Today we are going to debate on the material already presented, and we want to focus on the topic singularities in Einstein theory and black holes. So we are going to focus on the problem of something which is called a singularity in physics in general and also in Einstein theory. To this debate, I invited our main lecturer, Professor Klaus Kiefer from the University of Cologne. Hello, Professor
Hello.
Kiefer. And Professor Vincenzo Salzano from the cosmology group of the University of Szczecin. Hello, Vincenzo.
Hello.
Yes, we have heard a lot about the black holes. We learned something about the classical meaning and also quantum mechanical meaning. Just an hour ago, we heard also about the possible detection of the black holes or observational evidence for the black holes. But we want to devote this session to the more general problem, which was already mentioned during the talk by Professor Kiefer and also by Professor Biesiada. The problem is about how to deal with something which says that a physical quantity is infinite, and what we can do with that. In other words, we call all some things like this in physics just singularities. It was mentioned already the Roger Penrose and Stephen Hawking's theorems about singularities. And we would like to somehow mention how all this works in relativity theory. To start with, I would like to show something for the beginning of this debate. So our discussion is about singularities in Einstein theory and black holes. But let us perhaps discuss this. I just enumerated a couple of points, and my colleagues, expert, will probably comment more. So first of all, what are singularities in physical theories, one would say that it's the singularity is something which is related with the physical quantity, which blows up to infinity. There is some practicality behind this, because in the laboratory, we cannot measure anything, any physical quantity, which is infinite. Okay, the only thing which we can measure is something which is finite, whatever its value. This practicality simply tells us that our theory, which we deal with, should be corrected in a way or changed in a way to avoid this kind of singularity. And I can say some examples of the singularities. For example, if you take the Newton's force, gravity force between the two objects, so if these objects are very close together, since the Newton's law is inversely proportional to the distance between the massive points, then formally you can get force which is infinite. Similarly, the effect is also with the electric field. Since the electric field also, even if we write the force at the place where a point where the charge is, formally also it's the potential is 1 over the distance. So formally this value of the potential or force is infinite. So this is easy because in these classical theories, in these standard theories, we always can say something about the place. And the place is the point where the charge is, the place is the point where the mass is, but the space is defined. So we have a pathology, but the background is defined. It's unlike in Einstein theory, where, as we have seen yesterday and the day before and today, Einstein theory is based on the general relativity. Sorry, is general relativity, not is based. Einstein theory is just the theory of gravity. And the main issue, this slide is in Polish, but I think it's understandable. Geometry is matter. Okay, so we cannot define the geometry before we put some matter into somewhere. So the geometry is defined only in accompany with the matter. Unlike in Newton's theory or in Coulomb's attraction of the charges, we cannot say that something singular happens in space because space is not yet defined properly. Another issue is that then if we stick to this, that there is geometry and there is matter, if we stick to this, then we can somehow say, okay, we can differentiate between the physical field singularities, which is simply, as I said previously, mass, for example. So density blows up to infinity if we have very much mass at one point. uh, and geometrical singularity, where we have some geometrical quantities, like in Einstein theory, it is the curvature. The curvature is simply the bending of the geometry. So somehow these two types of singularities can be differentiated. So now let us move to what is invented in the Einstein theory, because we can, in Einstein theory, say something about some infinite quantities where some quantities which are related with the geometry of space are infinite. So somehow people were thinking that these points can be somehow treated as some extra points which are attached to the space-time, and they can be treated as boundaries of space-time, where there are some pathologies, and these pathologies are kind of analogy to what happens with the electric charge, where there is at the point where the charge is actually put, the value of the charge density is infinite, or force is infinite. Uh, if one looks at this carefully, people were actually having trouble in defining properly the singularities within the Einstein theory, because there were some pathological examples which couldn't be dealt with as kind of a boundaries of space-time. And that's why I think people invented the definition of singularity, which is based on the so-called geodesic incompleteness. What is geodesic? Geodesic in Einstein theory is the line in which you simply travel in space and in time. So we yesterday and the day before there were some plots of the space-time with the light cones. We also saw them an hour ago, drawn by Professor Biesiada. And what was invented properly by the people like Stephen Hawking and Roger Penrose is the definition of singularity, which doesn't somehow refer to any space and to any point in space, and in any does not refer to any physical quantity, except that something can be detected while we are traveling along this geodesic, which is our history of our evolution in space. So this is a kind of a minimalistic approach, but this approach allows us to say that there is a limit of the theory which is predicted by the theory itself. Okay, my colleagues, I somehow introduced, but I would like you to comment more, maybe Professor Kiefer, what you think is the most important out of all these issues I mentioned already here today. what you think about the definition of geodesic incompleteness, and what you actually what is your definition of the singularity in physics and in Einstein theory? And I know also that you are a fan of singularity within the framework of the quantum approach to gravity. So, can you comment on that?
Yeah, thank you, Marius. Yeah, certainly. I'm happy to comment on this. So first, maybe singularities generally in physics, as you mentioned, outside Einstein, of course, we have a background, and on top of it, there are maybe energies that formally become infinite. But infinite in that sense, for me, is always undefined, or you call it pathological. I'm in the line with, say, the mathematician David Hilbert, who wrote 100 years ago about infinities in mathematics and physics. And he entertained the point of view that there are no actual infinities in nature. And I subscribe to that. I would say this is an indication of a breakdown of our description. And for example, in electrodynamics, when without quantum theory, I mean, the electron spirals into the nucleus, and this is also kind of singularity, but this is then avoided by the quantum mechanics. So a more fundamental theory showed in that case that this singularity can be avoided. So as for Einstein's theory, yes, the general definition is the geodesic incompleteness. The reason is because that allows these theorems to be proven. But these incompleteness theorems that, I mean, the geodesic comes to an end, time-like or light-like, does not reveal the nature of the singularity. So I'm more in line, because you asked me personal, I'm more in line to what more recently George Ellis and others wrote. So for example, if you have this book, Relativistic Cosmology by Ellis, Martins, and McCallum, and maybe I cite a brief quote, because this is also how I understand it. So,
Mhm.
quote, we shall define a singularity as a boundary of space-time where either the curvature diverges or geodesic incompleteness occurs. Now, so, I mean, in this old book with Hawking of 1970s, it was not about curvature divergences. It was just topological. But the interesting physical situations are, say, Big Bang and also other cosmic singularities. I think Marius will tell about cosmic singularities later.
Yes,
And
I
yeah,
will comment. Yes.
yeah, and about a black hole. And this is where curvature usually diverges. So Alice et al., they then continue to write the relation between these two kinds or aspects of singularities is still not fully clear, but often they will occur together. Okay, this is very a physics language, not mathematics language. And I'm also a physicist, so I like this connection with the curvature, because these are the cases we study, that you and others, and I mean, we study about black holes and about cosmology. And of course, there are topological divergences, cones, no, with from gravitational waves. They're also of interest, but I think the focus is really on the curvature. And so your question, I
Uh,
answer,
uh, uh,
I would say in the way I just quoted Alice et al. I would say that would also correspond to me. Maybe I
so,
should mention there was a recent debate. I mean, Roy Kerr,
mhm.
who is, I mean, the discoverer of the Kerr solution that describes all the rotating black holes in the universe. And he discovered the solution in 1963 when he was very young. And he's still alive, and he wrote a paper last December where he criticizes heavily and strongly Penrose-Hawking theorems in a very, would say, direct language. We have discussed a little bit about that, and he has claimed that, yeah, there are incomplete geodesic in the Kerr metric, in his metric, that have a finite length, so they end, but there is no singularity whatsoever. Yeah, and but he defines singularity as a region where the metric or the curvature tensor are unbounded or not suitably differentiable. So that's also Kerr's definition because he says that's the physical definition. And then he comes with this case where there is an incompleteness, but there is no singularity there. So Hawking Penrose over exaggerate and so on. This was criticized also in the literature, and maybe I'm not competent enough to discuss the mathematical details. Um, but it is in line with what I said about the curvature, I would say. And certainly in the Kerr metric, we have inside this curvature singularity. But what Kerr mentioned was outside this singularity. So where geodesics are incomplete, but nevertheless, there's nothing physically happening. Maybe I'm already talking too much, so maybe I
Oh,
give
no,
back
no.
to you.
This is a discussion, so I will just ask some
Yeah.
provocative questions for the audience to have fun, because I understand that you are on a side that physics is important rather than mathematical proper formulation of
Yeah,
this
this is
singularities.
certainly my attitude. That
Or
of course mathematics is very important, and I like mathematics, but I always entertain the idea of physics first. So I mean, instead of
uh,
say theorems where you have maybe some differentiability assumptions and a lot of details,
Yeah,
and
so
so yeah.
okay, if one said, okay, there is some infinite value of the energy density, this
Mhm.
is more like physical singularity, not necessarily all these geodesic incompleteness issues,
Yeah.
because we cannot measure, in fact, uh, maybe with the clocks, okay, we cannot measure these geodesic incompleteness in the laboratory in a proper
Yeah,
way,
yeah.
while we can see that our measurement, our detectors will show or will reach their limit in the laboratory if we measure a quantity which is infinite, okay, or tending to infinity.
Yeah,
So
absolutely. I fully are on your side, what you just said.
but what you are saying is somehow kind of a very controversial because relativistic community I found was very fond, very keen on the definitions based on the Hawking-Penrose theorems. They
But this is
always
understandable. This is understandable because um, with that you can prove these theorems really mathematically in a precise and general way. Yeah.
Mhm.
So with a curvature singularity, I think I do not know of general proofs, yeah, that are as general as the Hawking, Penrose, and other theorems. Yeah.
To sum up about the black holes, so short for the audience, in your vision, what is singular, or what is a singularity of a black hole, in fact? What is meant by this singularity? What physical quantity is singular here? You mentioned curvature already, but
Mhm.
curvature is kind of geometrical. So
Mhm.
what is physically? Uh, uh, what is infinite there?
Um, Yeah, well, curvature, but curvature, I would say, is physical in a sense because you mentioned earlier that we can measure it in principle by having, I mean, the maybe the geodesic deviation equation. So in a detector with two particles and measure tidal forces, and these tidal forces, which are
Mhm,
already there in Newtonian mechanics, the
mhm,
tides, high and low tides. So they diverge in Einstein's theory if you are in the interior of a black hole. So a hypothetical observer falling in then would actually have this spaghetti type of extension of measuring rods and so on. And in the limit, when approaching the singularity, would then diverge. But my opinion, as I alluded to earlier, my opinion is that the singularities are a hint of a breakdown of the theory, and they are not actually there in nature. So as Hilbert already mentioned, they are not exact infinities in nature. And there's also a nice paper some years ago by also George Ellis and Nikolai and Meissner from Poland, who distinguish carefully between an actual infinity and just very, very large numbers. And so they argue that what we have in physics are only very, very large numbers, but that actual infinities, like Hilbert discussed, they are not really there. And you mentioned quantum mechanics. I do not know how much I should say about quantum gravity here, but
Just
if you,
give us a taste, a
yeah, a
taste.
taste. Okay, a taste
Maybe we
is
can shift this also for tomorrow, but give us a taste about
okay. Then a
quantum.
brief taste. Also later, maybe with the cosmic singularities, we discuss it. But the taste is that in quantum gravity is not yet a finished theory, but we can discuss models, and we can discuss models of quantum black holes. And in such models, one can construct quantum states where there is no singularity. For example, the following, what we also personally discussed and published. Classically, if you have a dust cloud, if this collapses under its own gravity, it can form a black hole. So there's a singularity, and there is this event horizon where nothing can escape. But if you go to some straightforward approaches to quantum gravity, what happens is that a dust cloud, if described by a quantum state, collapses, but does not form a singularity, but re-expands. And I think what is often overlooked is that Einstein's theory is time symmetric invariant. So there are black holes, and you see them behind Marius's portrait, the black hole. But
Mhm.
there are also the time reversal invariant, which is called white hole,
Mhm.
which we do not observe. And the quantum theory seems to know about this white hole. So instead of collapsing just to a black hole, you have a kind of superposition so that there is no singularity there and you have re-expansion. Okay, you may say, okay, this is rubbish. We don't observe this. Why do we not observe these things out? But this is a matter of the time scale. There is a large redshift, also gravitational redshift, so that from far away, I mean, there's a long time delay, and our universe is comparatively young, I mean, compared to this time scale. So it's not surprising that we have not yet seen coming out. Of course, we cannot wait. This will be maybe in billions of years, so we don't know. But at least on paper, I mean, you can have a nice looking solution where the singularity is avoided. And the hope is, and maybe Marius can also comment on that, the hope is that in quantum gravity, we can maybe avoid all of these singularities.
Okay, so it's clear that if something is infinite, it's rather the failure of our theory or of our mind that we cannot simply deal with this. So this definition based on the Nicolai and Meissner may be reasonable that there are just very large physical quantities,
Mhm.
values of the physical quantities, not infinities, because infinities simply say that we cannot reach the proper theory to describe this issue. Okay, you smoothly somehow made towards the Big Bang singularity because you mentioned white hole, and some people think that a white hole is just the Big Bang. And what you mentioned already, what is the black hole singularity? How about the Big Bang singularity? What is the Big Bang singularity then, and what you think it is, and how
Oh,
to deal with this Big Bang singularity?
Okay, very difficult question.
I know,
Um,
but it must be
but of course, we
difficult
all think about it, so I can say something about it. So, on the Big Bang singularity, usually you encounter in models of cosmology that are homogeneous and isotropic because we know that the universe as a whole, of course, is not homogeneous. We are there. I mean, there are structures, but if you go to very long scales, then it seems homogeneous. And this is why we usually look for solutions of Einstein equations that are homogeneous or approximately homogeneous. And given some energy conditions, the solutions lead to the fact that, okay, the size of the universe in the sense of typical distances between objects, say galaxies, if you go to the past, they go to zero. I mean, the universe, it's still there, and if it's infinite, it's always infinite. But these typical distances, they go to zero. And again, you have this curvature divergences, but also the divergence of energy, of matter, of say radiation or whatever you have. And this you see explicitly in this homogeneous model. So the singularity then, the Big Bang is everywhere in the universe. And assume we have a finite universe, then it's really then zero size. But if it's infinite, then it's always infinite. And then the whole infinite universe is a singularity. This is not intuitive. Yeah, and but it's you can do it mathematically. Now, of course, what is the Big Bang singularity when we are not in a homogeneous situation? I think there the situation is far less from clear because there we can have also local singularities and maybe there is no common Big Bang. I mean, the word Big Bang refers to this homogeneous picture, no? That everything is singular and then emerges. If this is not the case, if every place is different, then you can have a singularity here and a singularity there. There are some theorems that seem to suggest what happens when you approach the singularities. It's known under BKL singularity. This stands for three names: Belinsky, Kalatnikov, and Lifshitz, who did that long ago, decades ago. And yeah, maybe mathematicians should argue more about the rigor of this, but it seems that they show that if you go to the back in the past, then even if it's not homogeneous, so locally it looks like a kind of homogeneous anisotropic universe. So and that different space points are disconnected. Yeah, so it's a bit also of a complicated picture, but I think there is some
So
truth in that.
somehow you then say that even on the level of the classical theory, classical say not quantum relativistic theory, one should not think as kind of a cosmological singularity as the very general. Okay, this is
Yes,
your tran,
yes, yeah, yeah,
your statement.
yeah.
Okay, yeah, but if we touch just a regular homogeneous and isotropic universe, then we can say something that there are physical quantities such as the energy density, pressure, which are blowing up
Exactly.
when, excuse me, when you are dealing with this specific moment of the universe evolution. So maybe I just mention a couple before we shift into another physical issue. Let me mention that if we stick to the energy density here on this plot, it's in Polish, just
No problem. Yeah, I know what
uh,
type one and two
yeah,
is,
yeah,
so I
yeah.
can.
It's in Polish, but you have the quantities, physical quantities, which are energy density and pressure. Okay, everybody could understand what is energy density or just the mass density. Mass is energy, so in relativity is the same. Um, and there are a lot of cases which make I mean, in the past, people were thinking that only there is this Big Bang singularity, BB here, as a singularity in cosmology. In recent years, people revealed, while discussing the problem, also in terms of geodesic incompleteness, that there are possibility that some physical quantities reach infinity, like here. For example, we have the sudden future singularity type 2, where the energy density is finite, but the pressure is infinite. And this singularity is also geodesically complete. But what we deal with, we have simply the pressure, which is infinite. So in principle, we cannot measure it in the laboratory scale. There are also some other interesting singularities which in fact are geodesically incomplete anyway, like big rip singularity with energy density and pressure reaching infinity, but in some very specific way. But there are singularities like big separation type 4, in which only not pressure and energy density are finite or zero, and but the derivatives of pressure, this is kind of a mathematical meaning, and the derivatives of pressure can be translated into something which is called super acceleration. And this super acceleration is also very practically applied and in the case of the so-called car drag races in practice in American sport. I would like to mention by all this that the issue of singularities in physical theories, and in particular in astrophysics and cosmology, is much more complicated than it is generally, or it used to be generally said by the researchers in that field in the past. So nowadays we don't see the clear division of something which is singular and something which is non-singular. We somehow have the theory, the whole spectrum of different types of singularities. So somehow something is very strongly singular, something is less strongly singular, etc. And we even have the terms which are actually which were used for that, like weak singularities, strong singularities, etc. Okay, I think now after this we should give also the screen, the floor to our expert, Professor Vincenzo Salzano. I left some specific issue for him to discuss in this debate because what we were talking about mostly was kind of a static issue, but it was already mentioned during the lectures that most of the astrophysical objects rotate. And this is something which is in fact, the nature of gravity, that the celestial bodies rotate. I would like to ask Professor Salzano, is rotation a common phenomenon in the universe? Why is it so? And what rules the rotation of the astronomical objects? And what are the effects of these?
Yes, thank you. I have to say that in addition to what you say, that this discussion was very theoretical. I know that both of you, both Professor Kiefer and you, are very good and expert theoreticians. I'm not a theoretician, so I study what I can see. And
that's why we are having you here, okay? In order to avoid too theoretical discussion.
And for this reason, can I share the screen? Because I have some images or videos which I would like to share.
Yes, of course you can do. Yes.
Okay. So, yes. So the question was about if rotation. Rotation is everywhere in any form. And in order to start to understand why, I guess that we have to start from this picture, which is also the picture which you have on the background. Because I guess that the public nowadays is quite knows more or less what is the meaning of this picture. What they probably don't know is the mathematics which is behind and how can be painful to solve in some cases the equations which are behind this. But this picture and the one which you have behind is the present, the current understanding we have about gravity. So we generally talk about gravity as a force, but I have to say that many physicists, I would say the more fundamentalist or purist physicists, would say that gravity is not really a force, not at least not in the traditional sense. So what we have here is that the Earth is creating this well, and this well is not something which we can see directly, but we can feel because we are inside this well. This well and this grid, yes.
Can we make this full screen, please?
One moment.
Oh,
yes.
Excellent.
I was avoiding because I will have some videos, so it will go out. And by the way, so this grid, the grid which also you have behind you, is actually, we have to imagine it, that it represents what is called the space-time. So what you see there is that when you have a mass, it's going to distort, to change, to stretch both space and time. So now what is the point? Here on the bottom, you have clearly the sun and the earth. You can see that the well which is produced by the earth is much smaller, of course, because the sun is much more massive. So now let us imagine hypothetical that the earth is not moving, the sun is not moving. What happens? Well, we all know that if we have a small ball here close to this hole, it will start to fall down. So it will simply go down to at the center of this one. This is not rotation, of course, but this is the starting point. The starting point here, I had a video. Let me see. I already had it open because I wanted to avoid. This is the way gravity is visualized. So imagine that this is the sun, and then you have things which are not simply not moving, but they have some initial velocity. So what happens? They feel the deformation of, in this case, space, and they start to spiral. So you can understand that rotation in terms of, for example, the moon around the Earth or the Earth around the sun is something very normal, and it is connected to the fact that gravity, which is this deformation, can be said it is a central force. So pushes everything at the center of this well. Now, if you have some velocity, depending on the velocity, you can fall inside directly, or you can start to rotate outside, stable like the moon or around the Earth, or like the Earth around the sun, or you can simply pass and leave, like, for example, comets. Comets are objects coming from we say, the outer space, which feels the gravity from the sun, but not enough. They are very fast, so they just arrive in the solar system, and then they are moving, deviated. So I want to connect this with something else, because we are talking about gravity. We have named Einstein, but if we want to describe the gravity here, I guess that, and also in the high school, I guess that we don't study Einstein, but we study Newton. Newton was the guy who, while he was standing in English countryside below an apple tree, something happened, an apple fell on his head, and from this simple event, he understood how gravity works. Of course, this is just an aphorism. He was a great scientist, mathematician, physicist, so he already had in mind all the picture. And I have to say that we can understand the rotation and many other things from this picture. This picture was drawn more or less directed by Newton, and it is a thought experiment. Now, what is a thought experiment? It's an experiment which is only happening in our minds. It was done by Galileo Galilei, for example. It was used by Newton and also by Einstein. They are experiments which you cannot do practically, but they help you to formalize your theory and to let you understand some things. So what is this experiment which was thought? Let us imagine that we are on a very tall mountain and we have a cannon. And we are going to send, in this case, an apple, a cannonball. We are going to shoot something. What is our experience? That if I take a stone, for example, and I throw in the sky, it will fall down. Why? Because most of you know that it is because there will be the gravity, which is pushing to the center. Well, now imagine that we have a cannon so powerful, so powerful that not only it can shoot the apple very far, but at some point it can shoot the apple at such a velocity to exactly counterbalance gravity. What happens in that case? It might sound strange, but the apple will start to orbit around the Earth. And actually, it's not strange at all, because every time you use your smartphone, you are connected to some satellites. These satellites are say that they are geostationary. So what does it mean? It means that they are exactly doing what this apple is doing. So when you see these rockets, for example, now everybody knows Elon Musk and what he's doing. Of course, he has a lot of money, he has some vision, and he can do this. In the same way we play in our small room, he's playing in this way, also because of affair, of course. But when you see these rockets, which are launched, and you see all this fire, and you ask why they are burning all this. Yes, they are burning all this fuel because they have to do exactly what is done by this cannon. They have to give enough energy to the rocket in order to be free of the gravitational attraction of the Earth and orbit around the Earth. For example, everybody knows, because I know that there is an application which you can download on your smartphone, which tracks the International Space Station. The International Space Station is a space station, international because many countries participate in its construction, and you can see these passing during the night. Every night you will see a dot and it will pass through, and this is rotating around the Earth. Now, if I ask the public to imagine what is doing an astronaut inside the space shuttle, for example, everybody knows they're floating. And most of the people then think that they are floating because there is no gravity. Actually, maybe I'm going to destroy the fantasies of many people, but there is gravity. The only point is that there is nothing which tells them that they are falling. Actually, I want to be more precise. Astronauts are falling constantly on the Earth. But what is the point? The astronauts are like this apple. So they feel gravity, but they are fast enough to every time win gravity and maintain this orbit. So when you think about astronauts which are around us and they are floating, it's not because there is no gravity. They are not so far that they don't feel gravity. Actually, you can think astronauts are not farther than the moon. They are between the Earth and the moon. So how is it possible that the moon feels the attraction of the Earth and the astronauts no, and they float? Actually, they are rotating around us. And why this? Because gravity is a central force. And because they have enough velocity, because they are on this space station, which moves around us dozens of times around the Earth during the year, so during a day. So you can imagine how fast it goes, that they are orbiting in this more or less stable orbit, which is circular. What about the moon? The moon is the same. The moon is in another orbit, which is not a circular orbit, is elliptical, but it's the same. So when we talk about rotation, many people start to think circular. That's not the case. Circular, actually, the Earth around the Sun has an orbit which is elliptical. So imagine a circle and squeeze it a bit, that becomes an ellipsis. The moon is the same. So let me. So this was, and then why rotation is everywhere? Why the Earth is rotating? Why the moon is rotating around the Earth? Why the Earth is rotating around the sun? Why the sun is rotating? And if you go and if you look to galaxies, you will see galaxies, if you track stars inside galaxies, they will rotate. Why stars into galaxies rotate? And even stars, even galaxies can rotate. So why all of that? I have said here, this is a true simulation, which is done by cosmologists. It's not important that you understand what are these points. These points could be gas, molecules of gas. They could be stars. They could be planets. They could be galaxies. But what is important here is that this is a simulation. So you can see both on the left or on the right, what do you prefer? What is happening here? You have particles. As I told you, it doesn't matter what they are. They only feel gravity. What is happening? If you are able to track and to look at each one of these, what is happening? They are starting to move around each of these centers. Each of them has its own velocity. So it's like you have a lot of cannon which is shouting apples with different velocities. All of them will have its own orbit. Some of them will fall directly in the center of gravity. Others will orbit around. Others will start to have more larger ellipses. But what happens is that what you have here, you have a large blob of mass here, a large blob here and here. And what is happening now, that also these blobs of matter start to feel gravitational attraction from these other larger blobs. So gravity works at the level of the Earth. Let's say the Earth attracts the moon, the sun attracts the Earth. The center of our galaxy, of the Milky Way, attracts the sun, which actually rotates around the center of the Milky Way. And what about the Milky Way? Well, the Milky Way is not alone in the space. It's surrounded by other galaxies, and they are moving. Let's say rotating is not exactly rotation, but they are moving around another center of gravity, let's call it like that, which is somewhere in the universe. And this, if you take this volume, if you take this, it's called local group of galaxies, they are also rotating around another center of gravity. So what happens here is that at the end, all these blobs will be attracted to one single place, and there is where most of the mass is going to be concentrated. So let me close this, and let me come back to this one now, because this image, I put this image to let you understand how we arrive to this large-scale rotation to our rotation. This is in all physics books, we have this image, and also the public can understand, because I guess you have seen a lot of time these ice skaters, which rotate, and they start rotating with the hands and the arms extended. What happens when they start to close? Everybody knows, because we have seen many times, they start to rotate faster and faster. The more they close, the faster they go. So, why I'm saying this? Because this same process is why the Earth is rotating, why the sun is rotating. So everything started from a blob, as I show you in the previous simulation. There was a blob of gas, which started to collapse, as was said also by Professor Kiefer before. But now we're not talking about the dimension of stars. We're talking about dimensions of galaxies, for example. So what happens? This blob of gas is a gas. So let me say it's liquid. It's a gas. But what I mean to say is that it's not a solid, rigid body. So all the pieces of this cloud of gas, they are rotating, they are heating. What happens when it collapses? That it becomes smaller and smaller. So what is happening here is the same as the ice skater. Technically speaking, we say that the angular momentum is conserved, but the public does not need to know what is the angular momentum. Does only need to know that when this noob is collapsing, this gas, it's like transferring the initial rotation due to gravity to all these smaller structures which are inside. So why the sun is rotating? Because it was born from a cloud which was rotating around a center, and this center became the sun. What is the Earth? The Earth is part of the material which was rotating around the sun, the primordial sun, and it started to collapse. So, on one hand, you have the rotation of the sun, of the Earth around the sun, but on the other hand, is like the Earth itself, or the grandmother of the Earth, was rotating, and as it was collapsing, it was acquiring more and more rotation. So the Earth is rotating because initially there was rotation. And everything started because of gravity. And if you don't believe that the sun rotates, because of course, I guess that there is no fool here that has ever looked with his own eyes to the sun. But if you want to know if the sun rotates, this is an image which this is not an image. We have this, as you can see here, an NOAA is a satellite, which is the purpose is to study the sun. So what I'm going to show you now are photos taken by this satellite. And as you can see, when you put these photos in sequence, you can see that the sun is rotating. So the sun is rotating. And what about the Earth? Of course, the Earth is rotating because otherwise there would be no night and day. But if you want to see from outside, and also this is good because the Earth is not flat. Why? Because we can see it. This is from a satellite. We have a satellite. We put a satellite outside in a point, in a very specific point, and this satellite is taking pictures of the Earth for 1 year consecutively. So when you start to put in sequence all these pictures, you have the demonstration that Earth is rotating. So you have a demonstration also not from inside, but from outside. And here there is something very nice because this was taken also in 2016 when there was an eclipse. And you will see, for example, if Earth is flat, I don't know how you can explain eclipses, but here you can see, I will slow down maybe. No, I cannot slow down the velocity in this case, but at some point you will see a dark spot. This dark spot was the shadow produced by the eclipses. So we have here proofs that rotation is everywhere in the universe. And maybe some more smart person from the public could say, okay, so everything rotates. So also the universe rotates. Well, no. Actually, considering, taking into account all the observation which we have, the universe is not rotating. There is a model for universe rotating, and I guess that it was created by
a Gödel model.
Gödel,
yes.
Yes. And now let me make a joke. Gödel was a mathematician. So in his world, the universe could rotate, but nowadays we know that the universe, well, I cannot say that we know for sure 100%, but considering all the observation which we have, we can exclude that the universe is rotating for many reasons. The first one is that we can measure velocities of very distant objects. And we know that if we are looking at objects within the Milky Way, yes, there is rotation, but this rotation is different. It's because they are inside the Milky Way. They are rotating around the center of the Milky Way. So if we look to galaxies much farther, we are not able to see any rotation movement. But wait a moment, someone could say, okay, but if the galaxies are so far, maybe they are rotating, but we are not able to see this rotation, of course. The farther they are, the longer you should wait to detect the rotation. And considering how far are galaxies, you should wait billions of years to see rotation. And unfortunately, we are not able to wait billions of years. So there must be other proofs. Well, one proof which Uranus does not rotate is quite technical. Maybe you are able to give better details, but we cannot kill our grandfathers. And that's the point why universe does not rotate, because one of the consequences of the universe rotating is that we could travel back on time. So far, nobody has traveled back on time, which does not mean that it is impossible. It means just that so far nobody has done this. But then there is another thing, which is, for me, from my point of view, is the most striking demonstration that the universe is not rotating. What you see in this image is an image which you can get if you put a radio antenna outside and you start to scan the universe, the sky, you will get this image. These points, which are blue and red, just means points in the sky which are hotter if they're red, hotter or colder if they're blue. When you look to this picture, you can see that there are these, we call them fluctuations. So they are not large. Here we are looking to deviations from the temperature of the from deviation from an average temperature, which is 0.00001 degree. But it's important because there is a difference. Now, what is the point here? If you look to this, and if I ask you, do you see any pattern? Do you see any scheme in this? Well, the answer is no. And that's the correct answer. They are random. So if the universe was rotating, we should not be seeing this. We should see at least as sort. I have an image because there are simulations about this. If I'm able to take this off. So if the universe were rotating, we should not be able to see this, but we should see, depending on what is the rotation, we should see these other patterns which you see here, which we cannot see. So when you look outside, universe is not like this tree, but it's like this one. That is probably the biggest confirmation that the universe in total is not rotating. And I don't know, because I see that it is past 1, so maybe we can postpone other things later.
Thank you. Yes, there are lots of comments on YouTube related to your statements, but we cannot handle all of them at the moment. I will abbreviate them and will prepare maybe the answers tomorrow during the summary discussion. Yes, so let me try to conclude what you said, that there is a rotation in the universe on the level, but not the whole universe, which transfers into the rotation of the smaller and smaller objects, including Earth, Sun, etc. So this is what you, I think, mainly said. And this analogy with the ice skater rotating is just the best analogy to see it, how it works. Ice skater arms being closer and further. So this is the message you said, and also the proof that the Earth is rotating is wonderful, because some people may not, of course, we can see days and nights.
I would like to add something.
Yes,
because
please.
I told you that there is this satellite which takes images of the Earth. Now, someone in the public could say, wait a moment, but how is it possible that this satellite stands still, takes always the same image of the Earth, and is not rotating? Because if it's rotating, it should not be able to take these images. Well, we can make calculations, and we know that there are some few points in the system Moon, Earth, Sun, which are called Lagrange point, which are stable. What does it mean? That if you stay there, there is no attraction to the Moon, to the Earth, or to the Sun. So what we are doing, because when we want, the human beings are very smart, we have sent satellites and we have put them in these points. So they stay there and they are not moving from there. So this satellite is able to take always the same image of the Earth because it's in a point which is stable, does not feel any gravitational attraction from the system. And we have done this many times. So in case someone could say, but this is not possible because the satellite should be moving, and then these are fake images, fake videos. No, because we put the satellite in a point where we know that it stands still and can take these images.
Okay, thank you, my colleague experts. We have to somehow stop, and we will continue during the discussion too. Okay, in 20 minutes, so some of these issues may be still raised. So the next session is about physical effects in the neighborhood of black holes, but some of them are also related to rotation. So I think we can also continue. And also, if we have some questions or at least comments, we will try to handle them tomorrow during our final discussion, summarizing discussion session tomorrow at 11. So thank you very much for attending. I would like to mention that we are during the session Classical and Quantum Black Holes in the Universe, and our experts were Professor Klaus Kiefer and Professor Vincenzo Salzano from the University of Szczecin and Professor Kiefer from the University of Cologne. So I would like to invite audience to the next discussions in 20 minutes and tomorrow. Thank you very much. See you soon.
Yeah, thank you, Mario.
Bye.
Bye.
Bye.